Orbital diagrams is very similar, except remember, this is the one with the arrows. So let's try one. Let's do phosphorus. Alright, phosphorus' atomic number is 15. Atomic number is 15, so it has 15 arrows. So we go through the 1s. Okay? And if you want to do the electron here configuration here, that's fine. If you go back to your periodic table, you'll see it's 1s2, 2s2, 2p6, 3s2, 3p3. This helps some people. You're more than welcome to write this first, but make sure in orbital you write this as well. So let's just match it up. Arrow up, arrow down. 2s, 1 blank. Arrow up, arrow down. 2p. Anytime you ever write a p, doesn't matter what the number here is. What's a p? You go 1, 2, 3 blanks. Remember, you go up with the arrows first, and then you come back down. Now, I had 15 electrons. I've used up 2, 4, 5, 6, 7, 8, 9, 10. I've used 10 total. If you want to know what this number comes from, if you forget, the number of electrons is the same thing as the atomic number. So this is the number of protons as well. Okay? So we've used 10 up. We now go to 3s. Up, down. And then the 3p. This is an important part. Remember, p has 3 blanks. We have 3 electrons left to go up, up, and up. This is exactly how it should look. If it looks any different than this, you're wrong. Alright, try another one. Let's do vanadium. We're going to do vanadium. Vanadium's atomic number is 23. This means 23 electrons. If you're doing the electron configuration, and again, you're more than welcome to do this first to help you out. Some people it's helpful. You can match. Alright, so here we go. You go 1s. Arrow up, arrow down. 2s. Up, down. Oops, my pen's having a hard time writing. 2p, 3 blanks. Up, up, up. Down, down, down. 3s. Up, down. 3p. Up, up, up. Down, down, down. It's always good to check to see how many electrons you've used. I've used a total of 18 so far. Okay, so we're not there yet. So now we go to 4s. Up and down. Now I've used 20. I have 3 left. Now, 3d. Why is it 3 again? Remember, when you get to the d's, you subtract 1 from the row. Alright, when you have a D, you put 5 blanks over top every time. Remember, arrows go up, up, up. Uh-oh, I ran out of electrons. I can't use anymore. So there is orbital diagrams. Or there are orbital diagrams. Alright, noble gas shortcuts. Fast way of writing these. Let's try sulfur first. Okay, I want the orbital or noble gas shortcut for sulfur. So first thing you do is you find your element, sulfur. Now we're going to count backwards. So it Alright, let's try this again. The last video all of a sudden cut off here, so we'll start back at noble gas shortcut. Alright, noble gas shortcut. Let's look at something like sulfur. So to do noble gas shortcut, you first find your elements. We go here and we find sulfur. And you're going to count backwards to the group of noble gases. What I mean by that is we're at 16, so we're going to count 15, 14, 13, 12, 11. Keep going back until, boom, we hit 10. And if you don't remember this column right here, the last column, column 18, these are the noble gases. These are noble gases. So when I count backwards from sulfur, I hit the noble gas neon. And so for sulfur's noble gas shortcut, I'm going to put bracket neon, so put it in brackets. And then I'm just going to count forward from neon till I get back to sulfur. So I come through here. This is the third row, S, so 3s. There's 2 of them. And then I'm going to come through here, 3, these are the P's. And then 1, 2, 3, 4, all the way to sulfur. And so I write 3s2, oops, 3, that's supposed to be a 3 there, sorry about that, 3p4. It took 4 to get back over to sulfur. See, third row, 1, 2, 3, 4. So these are the p's, 3p4. Alright, to try another one, let's do a noble gas shortcut for vanadium. Vanadium's right here on the periodic table, so we're going to go backwards until we hit our noble gas. So vanadium's 23, 22, 21, 20, 19, boom, at 18 we hit argon, so our noble gas, so bracket AR, and now we're going to count everything else from AR forward until we get to vanadium again. So we go through potassium and calcium. That's going to be 4s2. Now go through here to vanadium. Now remember, we're in the D's. So though we're in row 4, we're not going to write 4, we're going to write 3, D, and then it's 1, 2, 3 over to it. And so we're going to write 3, D, 3, right? Because it's 3 over to it. 1, 2, 3. So there's no gas shortcuts. Alright, Lewis dot diagram. To do the Lewis dot diagram, we're going to need to label some stuff here because it's not labeled already. So sorry, I don't have room on top, so I'm going to label on bottom here. Alright, hydrogen, this is row 1, or also called 1A. I'm sorry, column, not row. Column 1. This is column 2, or 2A. We're going to jump over here. I guess I can go to the top here. 2 or 2A. This is column 3. This is column 3, or 3A. I'm sorry, 13, man. Whew, been a long day. 13 or 3A. This is column 14 or 4A. This is column 15 or 5A. Column 16 or 6A. Column 17 also called 7A. And sorry, I don't have room at the top, so I'll do it down here. This is column 18 or 8A. So to do Lewis dot diagrams, we just do the valence electrons. We talked about in class how to do it the longer way. I'm going to just show it the short way on this video. So valence electrons. Let's look at something like boron first. Alright, how to do it the quick way. Find the column boron is in. It's right here. It's in column 13 or 3A. And that lets us know that it has 3 valence electrons, because everything in this column has 3 valence electrons. So in Lewis dot, a valence electron are the outer electrons. We just do with dots. So it has 3. So 1, 2, 3. Remember, we go an electron on each side before we go back and compare them. So 3 dots. Now let's try another one. Let's look at nitrogen. Nitrogen's right here. It's in column 15 or 5A. And so all of these are going to have 5 valence electrons. So 1, 2, 3, 4. Now that we have one on each side, we go back and compare it. 5. Please make sure you do the electrons like this. Pretend there's an invisible box here. They go in the lines of the box. Don't write your dot out here. Alright, let's try another one. Let's do sulfur. Sulfur's in column 16 or 6A, so it has 6 valence electrons. So 1, 2, 3, 4, 5, 6. Boom, 6 valence electrons. Alright, we'll look at the last one. Let's do krypton. Krypton's right here in column 18 or 8A, so it has 8 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8. And don't forget, the most number of dots you can have, the most valence electrons is 8. Alright, nuclear. Let's go through and fill out this lovely chart. Alright, you might want to pause it and try to fill out beforehand, and you can see what your answers are, see if they match. But here we go. Alpha symbols 4 over 2 He. Beta 0 over negative 1 lowercase e. And gamma 0 over 0 with the Greek lowercase letter gamma. Alright, what is it? Alpha is a helium that's supposed to be a C. Nucleus, a helium nucleus. A beta particle is a high energy electron. And a gamma particle is a gamma ray. Another way you can write it is electromagnetic radiation. So gamma rays, electromagnetic radiation. Alright, penetrating ability. Alpha particle is very poor. can't go through much. Beta is moderate, and the gamma ray is very high penetrating ability. Alright, what can it block? What can block it? Remember, alpha can be blocked by paper. Beta can be blocked by aluminum foil. And gamma can be blocked by lead or concrete. Alright, we're looking at half-life here. When you do half-life, always have 3 columns. First column is going to be time. Second column is amount left. And our third column is going to be amount decayed. Alright, time is going to be 0. Always, and our starting amount is always going to be 0 for amount decayed. The amount left will always be our original amount, which is 2.0 milligrams. So whatever your amount you start with, that's always going to be the amount left. Time is always going to be 0. Decayed is always going to be 0. Alright, in this column here we're going to add half-life. So our half-life is 138.4 days. So 138.4 plus 0 is 138.4. Alright, in this column here we always divide by 2. So it's a half-life, so half of it went away. So we have 1.0 milligrams left. And this column here, if we just take this number and add it to the previous one, we'll get how much is decayed. So 1.0, I don't know what I'm doing there, milligrams. Alright, let's go through another half-life. So we have 138.4 plus 138.4. We get 276.8 days. So all I did, again, is add the half-life here. So 138.4 plus 138.4. Alright, we're going to half this again. So it turns out to be 0.5 milligrams. Take this and add it to the previous number, you get 1.5 milligrams decayed. Alright, add 138.4 again, the half-life. You get 415.2 days. And if you read our question, that's how much we're going for here. We got to half this again, so it's 0.25 milligrams. Add that to the previous amount, you get 1.75 milligrams. So we finished our chart. This question talks about the half-life of polonium being 138.4 days. How many milligrams is left? Alright, or will remain after 415.2 days. How much will remain is left? 0.25 milligrams. Second question is, how much actually decayed and went away after 27.68 days? So here's our 27.68. How much is decayed? Well, 1.5 milligrams. So there you have half-life. Alright, nuclear equations. Here we go. In this nuclear equation, we look at polonium-218. So let's go back and find polonium. It's right here. Atomic number 84. So when we do these, let's first see that, right, polonium, symbol PO. Mass number is 218. Atomic number is 84. Alright, it goes through alpha decay, so it produces an alpha particle, 4/2He. And a gamma. So there's gamma. Now, remember, the left side and the right side have to be equal, and they're not right now. I got 218 as the mass number over here. I just got 4 and 0. So 4 plus 0 plus what gives you 218? If you do that math, you'll see it's 214. Same thing with the atomic number, 84 on the left side of the equation, only 2 over here. So this number must be 82. 82 plus 0 plus 2 is 84. Alright, this is the atomic number, so if we go back to our periodic table, we can find our element is lead. And so we write down Pb for lead. Alright, this one, potassium, 43, goes through beta decay. If I find potassium, it's right here, atomic number 19. So 19. Alright, goes through beta decay, so it gives off a beta particle that's 0 over -1e. Now, those don't balance on each side of the equation, so there must be something left. 43 plus 0 is 43. This is the one you got to be careful with. This number down here is going to be a 20. 20 plus -1 is 19. And if I find the atomic number 20, I'll see it's calcium. So I write Ca, and this is how you do nuclear equations. Alright guys, that is the end of our review. Please study, and if you have any questions you can come in tomorrow for extra help. Fantastic.